Hey, I've got here another interesting integral. We've got the integral of 1 over square root of 3 to square root of 3 ln 2x over x squared plus 1 dx. Okay, it's interesting because natural log and x squared plus 1 don't work that well together. Maybe if it was just an x or just an x squared, but with x squared plus 1, I don't really see a u substitution working that well here. So what I tried instead is I noticed that these bounds are the reciprocal, right? We have square root of 3 and this is just 1 over square root of 3. So that inspired my substitution of u equal to 1 over x. Then solving for x, we have x equals 1 over u. I'll take my derivative. Derivative of 1 over u. We can look at 1 over u as u to the minus 1. So this derivative is going to be 1 minus u squared du. Then I'll make the substitution. And the nice thing here is when we do the substitution, it's just going to flip our bounds around, because when we plug a square root of 3 in here, we get 1 over square root of 3, and we plug 1 over square root of 3, we get square root of 3. Then we'll have natural log. For 2x, we plug 1 over u, and we're going to have 2 over u here. Then for x squared, that's just going to be 1 over u squared plus 1. We'll use our dx value, which is going to be minus 1 over u squared du. Well, I'm just going to use this minus sign here, and I'm going to use it to flip the bounds around. So we can swap the bounds, and now we're back to having our bounds the way they were right there. And what I'm going to do, let's distribute this in here. When we distribute a u squared in, this term's going to be 1, and this term's going to be u squared. So now our denominator is going to be u squared plus 1. So I'll rewrite this, but what I want to do here is I want to do a variable change, because I'm trying to set up where we can add these two together. So I'm going to change my variable back to x, which is fine because this here is a definite integral. So changing the variable name is not a problem at all. And what we'll do is we'll just call our original integral I, and then we just manipulate it down to this integral I, so I can add this to this. Noticing we have the same denominator now, same bound, same variable. And then from here, now that we've added these together, I'm just going to notice that we can use log properties on our numerator because we're adding this together. Just to be clear, we have this identity. If we have ln of a plus ln of b, we can rewrite that as ln a times b. So this is going to be ln 2x times 2 over x. But that's just, but when we multiply that together, the x's are going to cancel, and we're just going to have ln of 4. So when I rewrite this, let's write ln 4, but I'm going to bring it outside of the integral, right? But that's just a constant value. But I think one other thing before I continue on ln 4, we can write ln 4 as ln 2 to the 2. That's going to allow me to bring it up front here and write it as 2 ln 2. The only reason I'm doing that, I just want to cancel this 2 here so that we're solving for our answer now. And we'll just cancel a 2 here. Now what we have is a really well-known integral. Dx over x squared plus 1 is going to be just arctan. So I'm going to integrate this and see if I have enough space. So this will be our arctan of x. We just need to evaluate it from square root of 3 to 1 over square root of 3. And plugging this in now, arctan at square root of 3 is going to be just pi over 3. Arctan at 1 over square root of 3, or sometimes you might be more familiar with this as square root of 3 over 3 if you rationalize this. Anyway, arctan at 1 over square root of 3 is going to be just pi over 6. And then for our final solution, we'll bring over our ln 2. Pi over 3 can be written as 2 pi over 6. 2 pi over 6 minus 1 pi over 6 is just pi over 6. And so that's our solution. So that's it for today. Thanks everyone for watching. Have a great day.